Hello and welcome to my quick little discussion about Lesson 85, which is about acid and base theories. It's also the second half of the lesson is about something we call strong and weak acids. But what we want to look at here first is, what is an acid-base theory? Well, ever since they discovered that there were these things called acids and there were these things called bases, a lot of different scientists have come up with ideas of why something's an acid or something's a base. And so there's a guy named Arrhenius, and then there was a couple of guys, Bronsted and Lowry, and another guy named Lewis. Now, your book doesn't talk about Lewis, but I'm going to give you just a quick rundown on his idea because you might run into it somewhere in your future chemistry. But anyway, Arrhenius, what he said was that acids add hydrogen ions, these H plus ions, to a solution. And generally, this is the most basic definition of what is an acid. Okay, if H plus is there, it's an acid. Um, Bases, essentially, what Arrhenius said, add OH minus ions to a solution. Now, if you look at H plus and OH minus, what would you get if you brought those together? H plus, OH minus, you get two H's, one O, mixed water. We're going to talk a little bit more about the dissociation of water in the next lesson, and hopefully it helps a little bit in figuring out why this H plus and OH minus thing is so important. Now, what Bronsted and Lowry discovered about 30, 40 years later is that not all things that were acidic or basic fit Arrhenius's definition. And so they felt like they needed to broaden the definition a little bit in order to make the theory work for everything. And so what Bronsted and Lowry said is, okay, acids donate protons. And again, protons are typically the H plus ion. And they donate it to some other substance. That some other substance accepts it or picks it up. And this is what we call a base. The Bronsted Lowry definition of a base is that bases accept these protons from some other substance. And so if we look at ammonia, ammonia at first glance doesn't have any H plus, OH minus, anything in it. So it doesn't really fit the Arrhenius definition. We can't really see where is that H plus or where is that OH coming from. And so what Bronsted and Lowry said is that when ammonia and water gets together, again, water is the H plus and OH minus ion, the water is going to be the acid. It's going to donate an H plus ion over here to the NH3. The NH3, being the base, accepts that H plus and becomes NH4. That leaves the water. The H plus is gone. It leaves the OH minus behind. Okay, so it does in the in the Arrhenius definition add OH minus ions to the solution, but it was kind of unclear where that OH minus came from, and so that's where the Bronsted-Lowry definition comes in. Now, the Lewis definition gets even broader, okay? And basically, Lewis comes from our Lewis dot structures, if you remember that back in the first semester. But basically, Lewis just says, hey, acids are going to be these electron pair acceptors, and bases are going to be these electron pair donors. And I'm not going to get into it because it's not in your book. You don't have anything to kind of read on it. But it is kind of interesting because it takes some very, I would call them kind of exotic substances you're not typically going to run into. And it's able to show that by that definition, it is actually an acid or a base, whereas before there wasn't really any way to classify it. And so, kind of an interesting thing to look at, but it's not in your book. So make sure you understand the Bronsted, Lowry, and the Arrhenius. You don't necessarily have to understand the Lewis. All right, so let's finish this up talking about some strong acids and bases versus weak acids and bases. One of the big problems with acids and bases is that you can have a strong acid that will do nothing to you. Okay, you can have a weak acid that will melt your face off. It just depends on what is its concentration. And so the key thing that we're talking about is if we have a very concentrated acid or base, either a strong or a weak is going to do damage to you. Okay, so what we talk about when we talk about strong acids versus weak acids, strong acids essentially dissociate completely. They fall apart. And so what we see if we look at the reaction here, if I take some hydrochloric hydrogen chloride gas, put it into water, basically what is going to happen is it's going to turn into H plus, the hydrogen ion, and Cl minus, the chloride ion. And that's going to be floating in water. We can see that they're aqueous. That is a strong acid because most of what happens is that this, the HCl, completely falls apart. It splits into, I don't know if you want to call it dual personality, where it's got an H plus and a Cl minus. A strong base would be something like sodium hydroxide. Sodium hydroxide, we throw that into some water, and basically it completely falls apart into Na plus, the sodium ion, plus OH minus, the hydroxide ion. Again, the hydroxide ion is our base ion. But with strong acids and bases, the idea is that most everything goes to this side. Okay, what we say is the equilibrium falls to the right. And so everything is over here in its ionized form rather than being over here clumped like this. So maybe like 1 in a million is going to be like this. The other 999,999 are going to be like this. Basically, it's the opposite when we talk about a weak acid or a weak base. Okay, for a weak acid or a weak base, we don't have the dissociation. So this is vinegar or acetic acid. If we throw acetic acid into water, basically what would happen is that we get some H plus, our hydrogen ion, we'd get some acetate ion, again in water, but instead of most of it going here, most of it stays here. And so the idea is that we'd have one of these splits occur, and the other 999,999 would stay as it undissociated. Okay, ammonia, kind of the same thing. It goes into water. It would fall apart into NH4 plus and OH minus, but being a weak base, we get far less of this and far more of this. And so what that tends to do is that this at the same concentration, let's say we had a 1 molar concentration of this, that would mean there was a lot of this. If we have a 1 molar concentration of this, there's still some of this, but it's not nearly as much. So 1 molar concentration of this would be like a -1 on our pH scale. A 1 molar concentration of this might be something more like a 2 on the pH scale. So it just doesn't fall apart as much to give me these those H pluses when it falls apart. So again, I hope that's helpful. You guys know the action Wyrick at auhsd.net. If you need help, good luck.